Welcome to the class, and what we are going to discuss now is, we will continue discussing this rate matching, okay, that we discussed in the last class to a certain extent, okay. So we will finish discussing this rate matching, and we will take multiple examples, and with this we will try to wrap up this PDCCH transceiver chain also, okay. So the focus is on rate matching, fine. Again, so total number of segmented PDCCH segmented block is 1, okay. Courses are designed such that number of PDCCH bits G which can be transmitted are one of these, okay, correct, and number of bits which can be transmitted for PDCCH block, each PDCCH block is given by G by C, which is denoted as E, right, and since C is 1, E is same as G, okay. Right, and what we said was, okay, that this polar encoder length n, okay, this is basically what polar encoder will generate, okay, it can be greater or less than E, okay. So what we need to do here is basically rate matching. What are we saying here is that the number of bits which you are allowed to transmit is E over here, correct, okay, but the rate matcher is, but this polar encoder and subsequently sub-block interleaver is generating how many bits? Capital N, okay, right, N, and here you are allowed to transmit only E, right, and N can be greater or less than E, right, and that essentially means what, okay, that if then you are generating, if N is greater than E, you are generating more than what you are allowed to transmit, okay, you will have to drop certain number of bits. Correct, if N is greater than E. If N is here, E is here, if N is less than E, then you are generating fewer bits than what you are allowed to transmit, so you will have to basically repeat certain number of bits, okay, right, and typically rate is 1 by 8, this polar encoder rate is 1 by 8, so based on that rate can be higher or lower than 1 by 8, okay, right, okay. So but the key idea here is that based on the length L and E, this rate has to be matched, okay. And this is what we saw in the last class. Just for recap, what are we doing here? This is the formula, okay, and Nmax and Nmin. Nmin is the minimum polar encoder output length, and Nmax is the maximum polar encoder output length, okay. So we discussed this formula by first removing N1, okay, right, and we took this example of 140 bits, okay, DCI length is 140 bits, K is 164, that's the total payload which needs to be transmitted, okay, right. For downlink, maximum polar encoder length is 512 because capital N is 2 power N, which is 512, and minimum is 32, okay, right, and we understand this also, that the polar encoder mother code rate is 1 by 8, okay, right. So essentially polar encoder should be generating 8K output, okay, because if K is input and 8K, if length N is 8K, then rate becomes 1 by 8, okay. And what are we saying here? If you look at this formula, what does N2 decide? N2 is basically decides the code rate, and how does it decide the code rate? It is because it is equal to log of 2 K by R, and then ceiling, okay, right, and because 1 by R is 8, so it becomes 8K, okay, fine. So what are we saying here? If you look at N2, if you read this carefully, what is it saying? 2 power N2 is the smallest power of 2 which is larger than 8K. Larger than 8K because there is a ceiling, okay, right, and we understood this fact by taking K as, by substituting K as 164, what we get here is 1312, okay, right. So 2 power 10 is 1024, 2 power 11 is 2048, say that it lies between 10 and 11, okay, right. So it should be some number between 10 and 11, since we are sealing it, it will get 11, right, okay, that's what we are saying. 2 power N2, which is, N2 comes out to be 11, okay, which is 2048, is the smallest power of 2 which is larger than 8K, 8K is this, okay, right, that's how it comes out to be, fine, okay. So this is, now what are we saying, okay, if N2 comes out to be this, and we want the code rate to be 1 by 8, correct? Okay. Then we would like to code it with n is equal to 2048 bit. What will happen if you code it with 2048? Code rate will not be 1 by 8, it will be lower than 1 by 8, right? Because for 1 by 8, how many bits you need? 1312, correct? Okay. Because if 164 is the input, output should be 1312, correct? Then only the rate becomes 1 by 8, because k by n will become 1 by 8 in that case, okay? What are we saying here? Okay, that either we want 1 by 8 or a rate lower than that, okay? And for that n comes out to be 2048, right? Okay. Now the maximum which is allowed is the polar encoder length is 512. So you are not allowed to code at this rate, okay? What are you allowed? That's where this comes into picture, n2 n max, okay? N max is 9, n2 is coming out to be 11. So you restrict it to 9, because that's how the polar encoder has been designed for downlink, okay? So you get 9, fine, okay? And that's what we saw over here. So what happens here? So you get this factor as 9, okay? And then you substitute n min over here, you get, because n min is the minimum, of course this is greater than n minimum, so this doesn't play a role, right? Okay, fine. Now what we said here was that, okay, what role does n1 play? Okay, n1 is basically is a function of how many resources are allocated to you. And what did we understand, right? If fewer number of resources are allocated, okay, right, your polar encoder is will accordingly generate fewer number of bits, or the length n will come down, correct? Okay, if larger number of resources are allocated, n will increase, correct? Okay, that's what we saw here. So what is this? 2 power n1 is the smallest power of 2, which is larger than e, okay? And we took 3 examples. So if e is 432, okay, if for a user 432 bits are allowed to transmit, what you get n1 is, just substitute it over here, you will get 9, okay, right? N becomes 9, okay, you substitute it over here, 9, 11, 9, you get 9, okay. So what will be the polar encoder length? 512, okay. Now what are we saying here? Okay, for the same payload, if another user is allowed to transmit only 216 bit, why should polar encoder generate larger number of bits when it is allowed to only transmit? The maximum comes out to be 256, right? Correct, because how many bits for this user it is allowed to transmit? Only 216. So polar encoder will accordingly generate only 256 bits. Here it is allowed to transmit 432 bits, accordingly n is increasing, fine. And we took one final example. What does it tell? Even though you are allowed to transmit more number of bits, because for downlink, polar encoder can generate only maximum of 512 bits, okay, right? Even though you are allowed to transmit 864 bits, you cannot generate more than 512 bits, because the restriction is imposed by the standard that for downlink maximum is polar encoder length can be 512. And how is it coming out to be? That's where n1 plays a role over here. This is n1, okay? In principle, right, you would want it to be 1024, because if the maximum is 1024, if n is 10 over here, right, what will you get over here? 10. And that happens for uplink, because for uplink n max is 10, right? Okay, so you'll see that it will come out to be 10. But here, since the maximum polar encoder length is 512, you are restricted to 512, even though you are allowed to transmit higher number of bits than 512. What will happen in this case? What will rate matcher do? Rate matcher will repeat bits. In both these cases, rate matcher is going to drop certain number of bits, right? And that's an example we are going to take, okay? Everything will fall in place now, okay? So what are we saying? DCI length is basically 140. With k it becomes 164. I'm sticking to the same example, 164. G is one of these, okay, and I'm going to pick up those numbers only, 432 to 864 216, okay. So the first example we picked was core set is chosen such that G is equal to 432 bits, okay. E becomes how much? 432, C is 1, correct, okay. You have to decide polar encoder length, n, or equivalently small n. What did we did this exercise, all 3 examples we took in the last slide for this particular reason, okay. So what happens? For this configuration, n will be 9, which was calculated in the last slide. Therefore, capital N is 512. Fine. Now what is E? 432. This is the number of bits you are allowed to transmit. But you are generating 512 bits. Okay. We will have to drop these bits at the transmitter. Okay. Right. So what is happening here? What is the rate at which actual rate what it becomes? Rate will become K by E. This is the actual rate which is asked by the user. Correct? That's what you are finally transmitting, because E is the number of bits which you are transmitting for this user, and what is the payload? K. It will become K by E, so it becomes 164 by 432. The rate is 0.379. Okay, right? But actual rate, how much you are generating in this case? Okay, 164 by 512. Get that? Okay. If you are generating at a lower rate, because it is 164 by 512, right? At what rate your polar encoder is generating now? This is this, right? At what rate polar encoder is generating? K by n. K is 162, 164, and n is 512. This is some number. Okay. And at what is the rate the user has asked? K by E. That's how these resources are allocated. 164 by 512. You are generating at a rate lower than what user has asked. Right? Okay. Correct. What does that mean? You are generating more parity bits than what user has asked. That's what it means. So you'll have to drop certain bits. Okay. Correct. That is one way of looking at it. Another way of looking at it is basically again the same thing. Okay. That you are like E is basically less than n. Correct. Okay. Right. You are generating n bits, but you are allowed to transmit only E bits. Okay. What will happen? Okay. That user rate matcher will have to drop certain number of bits, and that's what I am going to show you. But what is happening here? The core set is carefully chosen based on the MCS reported by the user. Okay. Right. What is the point here? That what is E? You look at this 432. Okay. So user would have reported an MCS around this number. Okay. Right, or an MCS higher than this. Okay. Because if you remember, for control chain, okay, you want to always transmit at a rate lower than what is transmitted for what is used for the data, because you want control chain to have more protection than the data chain or the PDCCH chain. Okay. Right. So most likely for the data, the rate which will be used for this user will be higher than 0.37. Okay. But for the control chain, it is around this. Okay. Right. So core set is chosen typically based on the MCS reported by the user. Okay. Now there are 2-3 cases. Okay. So what are we saying here? Standard uses two different terms. One is called puncturing. Okay. First we'll understand this. Okay. What is puncturing? So both of them drop the bits. Okay. So what are we saying here? If E is less than n, that's what is happening. Correct? That's what I just showed you. What is E? Right? E is 432 and n is 512. So E is of course less than n. We have to drop certain number of bits. Okay? Right? So if E is less than n and R is less than 0.4375, this is a number given by the standard, then mother code is punctured. I'll explain you what is that. What are we saying? So this is the condition which is happening here, right? I just calculated the rate here. How much was the rate? It was lesser than 0.43. It was 0.36 or 0.37. Right? So this condition is satisfied. So in this case, rate matcher is going to puncture the bits. And what is this puncturing? It will drop certain bits from the beginning. Okay, not from the end. So what is this rate matcher? Rate matcher is again a circular buffer of length n. That's what it is. Okay, right? So what are you doing? You are taking n bits which are generated by the polar encoder and you are writing them in a circular buffer. Your circular buffer is a rate matcher, or a rate matcher is a circular buffer. Okay, that's what we are doing. Okay, how many bits you are allowed to transmit? E. Okay, and since E is less than n, you have to drop certain number of bits. Instead of dropping the bits from the end, you are dropping those bits from the beginning. Okay, and standard calls that as puncturing, or that's the term which is used. Okay, this is called puncturing. Okay, and why is it happening? So what are we saying here? First n minus E bits are not transmitting. We are not transmitting those bits, not from the end. We are dropping certain bits from the beginning. And what is the reason? For polar codes, puncturing works better for low code rate. Okay, so this rate is actually on a lower side. Okay, higher is basically if the rate is higher than this. Okay, you call that a higher code rate in context of this. Okay, what are we saying here? If the rate is less than this, you do puncturing, and what is puncturing? You drop certain number of bits from the beginning. Okay, if the rate is higher than that, do some other operation. That's what I am going to show you. Is this clear? Okay, in the first case, we are dropping these bits from the beginning, not from the end, and this is the condition. Okay, let's look at another example. Second example. Okay, everything is remaining same. A is 140, payload remains 140. Once K becomes 164, G is this. What am I doing here? I am choosing G is as 216, right? Immediately you should be able to understand that this user has a better SNR than the other user, because it is asking for fewer number of bits to be transmitted, right? Okay, what are this? So E becomes 216, correct? So you look at the rate, K, what will be the actual rate? Rate will be 164 by 216, right? Okay, correct? In other case, it was, in the last case, 164 by 432. So it's basically the rate is double, right? Okay. So decide the polar encoder length. We calculated it, and how much it came out to be? 256. That's the second example I took, right? You remember, in the first example n was 512, in the second example it was 256, right? Okay. So E is less than n, but what is E? 216. How many bits you are generating? 256, right? Since user is allocated only 216 bits, why will polar encoder generate 512? That's the message we got it, right? So it will generate only 256 bits, but still it is higher than G, right? Okay, so what is rate now? 0.64, 164 by 256. The rate becomes double of what we saw last time, 0.6, and it is greater than the number which I gave you, right? Okay, so if E is less than n and R is greater than 7 by 16, okay, which is 0.4375, which is happening in this case, mother code is shortened. That's the another term which is used, okay? And what is the shortening? It drops certain bits from the end. N minus B from the N minus E bits from the end are dropped. Okay? And what is the reason? Okay, that's the reason I gave you, right? If the code rate is higher, then you do shortening, because for the polar encoder, that is good. If the polar encoder has to work at a higher rate, you drop certain bits from the end, not from the beginning. These are the two cases which are considered, okay? But in both these cases, what are we doing? We are basically dropping the number of bits. Other what case is left in which you have to wrap around and reread the bits, and what is that case? Okay, your generator at your polar encoder is not generating sufficient number of parity bits, okay, right? That's what it is. A is equal to 140. Again same, this configuration remains same, right? Okay, and what example we took? 864, right? That was the third example for which we calculated the polar encoder length. Okay, what is it coming out to be? So what will E be? It will be equal to G by C, which is 864, okay, right? So polar encoder length we calculated. What will come out to be? 5112. It's coming from the first slide or the second slide which we took in this class, okay? E is greater than n, right? You will have to repeat bits at the transmitter. What is this? That's what it is. What is the circular buffer length? N, that doesn't change. E is greater than n now. So what will happen? You will wrap around and keep reading till you reach n bits. You see this, okay? You will keep reading till you hit E bits. Okay? This is n. What are you saying? This is a rate matched polar code block, okay? So you have basically read these many extra E minus n bits from here, right? Okay, because polar encoder is generating fewer bits than what you are allowed to transmit. N is 512 in this case, okay? You are allowed to transmit 832 bits. So it will read 832 minus 512 bits extra, 320 bits extra. This is that 320. Wrap around, okay? Right? So these are three different possible cases for the rate matcher, depending on how many bits are allowed for a user. And that's how it is given in the standard. I'll just take 2 minutes. So bits encode output from sub-block interleaver is given like this. Remember? Okay. Rate matcher, this becomes input to the rate matcher. Output of the rate matcher is E. Okay. Right? So there's a typo. It should be E1, E2, E3. Okay. Right? And how many? So what is the input to the rate matcher? N. Output of the rate matcher? E. And this is how it is specified in the standard. If E is greater than N, then you do repetition. We see this, we saw in the PDCCH block also. There is a modulo, it will wrap around, okay? Those many bits you are going to read, correct? Else, if K by E is less than 7 by 16, you do puncturing, that's the first case. Otherwise, you do shortening. What are you doing here? Okay, you are dropping bits from the beginning, otherwise you are dropping bit from the end. You are running, where are you running from? K is equal to 0 to E minus 1. So you are reading E bits, but from where? Look at this index, you are offsetting it, right? Offsetting it by how much? N minus E, right? If K is 0, what will be, so what will Y become? It will become N minus E. So you are dropping N minus E from bits from the beginning. That's the offset. and then you will write in the output buffer. Correct? Okay. For the shortening case, you will start reading from the beginning. That's all. And how many bits you are going to read? E bits. Okay. And the rest of the bits remains, get dropped automatically. This is the offset which comes here. This is the repetition, and this is the rate matcher for the PDCCH block. PDCCH block. In the PDCCH, none of this is required because there is only consistently you drop bits from the beginning. Right? Okay. So a separate rate matcher has to be designed for this because polar encoder has different characteristics than LDPC encoder, right? Okay, and these are two different characteristics of a polar encoder which are not there for LDPC encoder. Okay, right? So we'll stop here. This brings us to an end of the rate matcher discussion. Okay, so we'll continue discussing from here in the next class. Thank you.